This is the seventh and final lesson for unit number 6, and we're going to look today in this lesson at something called Newton's law of cooling. And it's the story behind things like this piece of iron that's been in a furnace and it's very, very hot. And as it comes into the room, it's going to start cooling off and its temperature is going to drop. But the temperature drop is very quick at the beginning because it's so much hotter than the room and the heat flow is very high. But then as it gets down closer to room temperature, that temperature difference between it and the room is smaller, and so the heat flow is a lot less. It's a lot like the exponential decay solutions we saw in the previous lesson, but there's a big difference. It won't go right down to zero eventually because the room temperature could be much higher than 0 degrees. But it's going to look very similar to that exponential decay. So first of all, what's it all about? Newton's law of cooling is when the rate at which some object is cooling is proportional to, now if this was just exponential decay, we'd say to how hot it is, but instead I'm going to say to its difference in temperature to the room. So that's going to be a big issue. How different is its temperature to that of the room? Okay, so let's talk about the variables that we're going to have in this story. A is going to be the surroundings temperature. So I'm going to have my little graphic here just for a minute, and then I'll take it away. A would be like the temperature maybe of this anvil, right? Some room temperature that's out there. Capital T is going to be the temperature of that really hot object, right? So that's capital T for temperature, and it's a function of time, right? So you've got your clock running, right? That's keeping track of time. And what we're going to see is this temperature is going to start to drop off. So that capital T is going to vary with time. And I'll tell you just what it looks like in a nutshell right here. If it was just exponential decay, like radioactivity, then the temperature would go and decay down to 0. But what we're going to see with Newton's law of cooling is it doesn't do that. If the room temperature is right here, then it's going to decay down and get closer and closer to room temperature. So it's like exponential decay, but with a little bit of a lift to it, right? Some sort of elevation to it, some sort of transformation. And the differential equation that we're going to play with will do exactly that. It's going to lift that up and everything will be great. Okay, so let me get my doodling out of the way, and then we can actually get down to business here. So capital A is talking about, again, the temperature of the room, temperature of the surroundings, and then capital T is going to be the temperature of the item. And that's the one that's going to change as time goes by. And we'll say that the room temperature doesn't actually change. Okay, so a few little thoughts here. The differential equation that talks about the changing temperature of that hot piece of metal, it's going to say that the rate at which the temperature is changing, so that's dt, it is proportional to, so it's equal to some constant multiplied by, but I'm not just going to put a t here. That would be exponential decay. That would go down to 0. I have to say it's proportional to, what did we say up here? How different it was to its surroundings. So it's proportional to the temperature minus the room temperature, right? How much warmer it is. Now, if you've got temperature of your object, that when you subtract the room temperature is still positive. In other words, another way to say that, if the temperature of the object is greater than room temperature, then you're going to find that the object is very hot and it's going to be cooling off. If when you go temperature of the object, subtract room temperature, it's less than 0, if it's negative, then that must mean that the temperature is below room temperature. Then you're going to find, kind of like ice cream, if you leave it out, it's going to warm up. If that difference in temperature, let's not worry about plus and minus for a minute. If that difference in temperature is very, very big, then the heat transfer is going to be very fast. We'll quickly be changing temperatures. And if the difference in temperature between the object and the surroundings, the object and the room temperature is pretty small, the heat transfer will still be there, but it'll be very, very slow. Okay, we're going to try to solve this differential equation, but I'm going to leave this picture sitting right here, blocking out this part of the notes because I'm not even going to do this little issue with the trick anymore. It's not worth it. I think we can actually just do this quite nicely as a separable differential equation. So completely forget about that little section there, and instead we're going to dive right into how we can come up with the solution in a nice, quick way. So yeah, steps 1 and 2. We won't worry about those. Let's just go over the page and we're going to start to look for the solution to this differential equation. So we're going to kind of use the space on this page here creatively because the section headings don't really make sense anymore. First of all, let's just rewrite this differential equation that we've got. It says the rate at which that material is cooling, dt dt, is actually proportional to, okay, it's K times capital T minus an A. Now, just to clarify, you've got some constants here. This K is a constant. We're going to find out that it's negative. And this A, the room temperature, that's also a constant. We're going to see if we can eventually come up with, what capital T is as a function of time. This is a separable differential equation. You have got that dependent variable, the important variable here on dt dt, it's right up there, and it's also showing up on the right-hand side. So let's actually do the separation of variables. Let's put the capital T term over on the left. And when we do that, it's going to look like this. 1 over that important variable minus a constant, d capital T, is equal to K times d little t. And now we're going to go and we're going to integrate. Now, if you really want to, you can do this by a substitution. Okay, you could say, oh, I'm seeing a little blob there. And you could say, all right, that blob could be capital T minus A. Capital T is the main variable there. And then you could do a dB dt, and you'd find, well, that's just equal to 1. So dBs are equal to dTs. And you could make a total switch over to Bs. And once you've done that, what you're going to find, I'm just going to, again, use this space here creatively, right? Not really paying any attention to the section headings anymore because we're kind of changing the way we're doing this, right? So totally ignore what these words are. Okay, these two. Okay, at this point, you could then integrate both sides, and you're going to find that you end up with a ln of this t minus a. Okay, that's what's going to happen there. So you would have ln of t minus a is equal to kt plus c. This is very, very similar to what we saw in the previous lesson for exponential decay. And then when we go and try and solve for capital T, we're going to have to exponentiate both sides. And we're going to end up here with t minus a is equal to e to the kt plus some constant, which we usually write a slightly different way. We say, well, why don't we write that as some other constant, so it's not quite the same c, and then e to the kt. Okay, so not exactly the same c here. This is that whole without loss of generality thing. That's constant 1, that's constant 2. Now, I really want to get that capital T all by itself, so I think I can do it if I actually just say, okay, let's move the a. It looks like capital T, the thing that I'm looking for, which is a function of time, right? Depends on what time of day it is. That capital T will be, let's move the a. We're going to have a plus, and then over here some constant, e to some k times t. So we still have some constants that we have to go and figure out, right? There are actually 3 constants here. This a is just room temperature. That's no big deal. And then there are a couple of other constants that are yet to be figured out, yet to be determined, and that would be this k and this c. Well, one of them we can actually figure out right now. Let's call the original temperature, the temperature at time 0, let's call it this t with a little 0 down there. Let's call it T0 as it's pronounced. Okay, so that's all that this T0 is. When you see that there, it's like, hey, what's this T0 thing? It's just the initial temperature, okay, the temperature at time 0. Well, when you start putting in time being 0, this whole thing tidies up pretty nicely. You would have this. Okay, temperature at time 0, we're calling that T0. That would equal A plus this C. I'm trying to find that C. And then e to the, I'm trying to find this k too, but don't worry, we're going to multiply that by 0 right now. So we don't have to worry about the k for a moment, because k times 0 would just be 0. And then e to the 0 is just a 1. And so I end up with this story that the original temperature of that hot iron as it comes out of the furnace It's equal to A, room temperature, plus C. Oh, okay. So it looks like C, this constant that we're trying to find, it's actually just the original temperature of the iron minus the room temperature. Some people would say, hey, this C, it's the original difference. Write that down below where it'll fit a little better here. So if the room temperature is 20 degrees Celsius and you pull this piece of metal out and maybe the piece of metal's at, let's just go up to 50 degrees Celsius. Well, 50 is originally 30 above 20. So the capital C would be the 30. Okay, so putting this all together, it looks like for Newton's law of cooling, when you take hot things out of a furnace, the temperature later on in the day, it's just equal to room temperature plus this original difference, T0 minus A, and then e to the kt. And that k just depends on the geometry of the story, and we're going to see that it basically will be a decay, so that k will be negative. It'll happen all on its own, that a negative sign will show up there. So the original temperature difference between the body and its surroundings, that's this part right here, this original difference. That's what this is talking about. That just decays away, right? That's what the e to the kt will do. It'll just make it disappear. And sometimes people like to ask you to do this neat little limit. And they say, okay, well, what if we do a limit for the temperature of the item, right? So they're trying to ask you, what's the temperature going to do when time goes to infinity? Okay, so in other words, just wait a long, long time. Well, think about that for a minute. If you take something hot out of a furnace and just put it in the room and then wait, forever, what will the temperature be? Well, I kind of have a pretty good idea in my mind, but let's think about this story here. Looking at the big equation in this black box, we're trying to do the limit of room temperature, that's a constant, plus this original elevation, how much we are originally warmer than the room, and then this e to some negative number, k is negative, multiplied by t. Well, if you look just at this part right here, this e to some negative number multiplied by t, I mean, I can even do this on my calculator, right? If I take e and then I have some negative number here, right? Like, I don't know, even if it's small, like -0.03. And then I start multiplying by time, okay, going across sideways. If I graph that, let's just take a look. Let's try graphing it. Right? What would this be? E to the some negative number multiplied by x, and we'll see what that looks like. I might have to try a couple of zooms here, but I think we can get a feeling for this. So here's this exponential. Whoa, geez, it kind of looks like it's just dropping off there. Let's go to a bigger window. Let's let time go a little bit farther. Let's go out to 20. See what that looks like. Oh, it's just dropping and dropping and dropping and dropping. Okay, let's go even a little further. Let's go out to like, I don't know, 100. Tick marks maybe every 10. That is just, it's decaying down to nothing. It's going down to 0. So when I go to do this limit, if t is going to go out to infinity, a negative infinity here, that's an incredibly small number. That will destroy this T0 minus A. So the original difference, the amount that the item is originally up above room temperature by, that just goes away. And all you're left with is room temperature, just capital A. So if you do a graph of this, it looks basically like exponential decay, but it doesn't go down to 0. So this might be a graph of temperature versus time. And it looks like in this story that room temperature is right here, okay, at that A, maybe 20 degrees. And here's that original difference right here. Right, that would be the T0 minus A, because it looks like we're starting up here in this little sketch at 80. And 80 is originally 60 above 20. Right? So that's all that this T0 minus A does. That's it. It would just say, hey, did you notice that you were originally 60 above room temperature? and then that 60 decays away. Like at the beginning, you can see, hey, we're 60 degrees above room temperature. And then you wait a little bit. Uh-oh, look, now we're only 30 degrees above room temperature. Then you wait a little bit more. Uh-oh, look, now we're only 15 degrees above room temperature. And then here, oh, now we're only 7.5 degrees above room temperature. And it's just that half-life story. It's just going to get smaller and smaller and smaller. And we're just going to end up decaying down to room temperature. That's what Newton's law of cooling and then stories like it are all about. It's an exponential decay, but with this limit of some value that isn't zero in the very, very end. Let's try out two examples, and then we're going to do one that's not about cooling. It's actually going to be an old AP exam question. But first, two temperature examples first. So we're just over the page. It says a can of hot water starts with an initial temperature of 80, so that's pretty hot, in a room that is at a constant temperature of 20. And then when you get to 20 minutes down the road, the temperature of the can is now down to 35. And you have to find the temperature solution just as a function of time. And it says, please do it by separation of variables. Okay, sure. Yeah, we can do that. I'm going to need a little bit of space though. So I'm going to take this room that I've got and then just divide it up in half here. Just trying to make some room. Okay, so we'll go right from the beginning. We're really just practicing this separation of variables, right? That's where we're trying to go with this. So the story for Newton's law of cooling is the speed at which it's cooling. That's that right there. It's a derivative of the temperature. It's going to be negative in the story. That's going to equal some constant multiplied by how much hotter this thing is than the room. So it says we've got this room temperature of 20, right? That's our A. Okay, they said please do a separation of variables. No problem. Let's move this capital T term over to the other side. We're going to have 1 over T minus 20, and then dt is equal to K, and then we'll bring the little dt up to the other side. There they are, they're separated. Now we're going to integrate both sides. Now, we've done this kind of integral on the left a few times. I'm going to doodle over here just for a second. Just going to make a mess. You know, we know, of course, that if you're doing that one, that you're going to end up with just a lawn, right? That's how that one's going to go. Well, that's all very nice if it's just an x down there. We've got this kind of like x minus 20 in this story. But we've seen what happens. You can do this by integration by substitution if you want. But in the end, it ends up looking like this. The ln of t minus 20. You know, if you do a derivative of that, you'll see that the chain rule doesn't really kick out anything that's annoying. So we don't have to put any little constants in there, any little bodyguards. We're totally fine. Now, I guess we should be like, oh, absolute value, but we're going to actually have a positive value for that, so it's not going to be a problem at all. Okay, and then that's going to equal over here. When we do our integration with little t's, we're going to get k little t plus some sort of constant. Okay, well, that's all very nice, but I want to know what capital T is. And I'm not worried about the absolute value bars because this is going to be a positive number. Okay, I'm going to now go and exponentiate both sides. I don't want to look at the ln of capital T. So if I exponentiate, t minus 20 is equal to e to the kt plus c. Looking good. What I want to know is what's capital T, and I'm pretty annoyed by the way this c looks there. Let's deal with this c right away. This is a move we've done many times here now. We're going to think of that as being e to the kt times e to the c. I just don't like the appearance of that c up there in the exponent. It just really doesn't work well for trying to find its value. So I'm going to reposition it. T minus 20 is equal to e to the c times e to the kt. Let's go with a whole new constant. Let's say t minus 20 is equal to some other constant, e to the kt. Those are not exactly the same c's. And if people ever, get upset with you on that, you can just say, hey, come on, without loss of generality, it's okay. Hey, we're just about there. We've got t minus 20 is equal to, sorry, I'm going to move that 20. It's time to do that. T is equal to 20 plus, okay, I've got to find this constant, got to figure out who that is, and then E, oh, and I got some other constant here, I've got to figure out who that is, times T. I mean, we're super close. All we need to do now is just find those two orange things, and we'll have this whole thing dialed in. So I'm going to go back up to the other side, and I'm going to start to use some of the bits of information I've got to find out those values. And the capital C is the easiest. If I think about what happens at time t is equal to 0, my equation down here, if I put 0 in for t, oh, it starts to look really nice. It would actually say the temperature, which they're telling me is 80, right? They're saying, oh yeah, you're going to start off with 80. That's equal to, let me look back down here, 80 equals 20 plus that orange C and then E to some K that I don't know, but multiplied by a time of 0, right? I'm just taking the story down here, putting 0 in for this T. Okay, great. Well, K times 0 is 0. E to the 0 is 1. So it looks like we have 80. This is not a surprise to me. It's kind of doing exactly what I thought, because we talked about how this C is going to be the original temperature difference. And what I find is, yep, it's 60. That material was originally 60 up above the room temperature. Okay, so we're getting closer. I could rewrite this formula now. Instead of saying 20 plus C, how about we say this? We're getting close. The temperature is equal to 20 plus a 60. E to the, okay, there's still one more mystery. That K times T. We're close. So let's go and grab some more information. This K is all about just the geometry of the story, and it's going to decide how fast it cools. But they gave me another clue. They said when little t, the time, is 20 minutes, you got to be down to 35. Okay, well, let's throw that in and see what happens. Okay, let's go with t being 35 for a second. Sorry, did I say that wrong? Yeah. Capital T is 35. Little t is 20. All right, capital T, 35. That's our temperature. That's equal to 20 plus a 60. E to the, I'm looking for K, times the temperature, time, oh, I keep mixing those up, times the time of 20. All right, we're solving for a little K. Not too bad. We can move the 20 right away. Looks like we're going to have 15 is equal to 60. E to the, if it's okay with you, I'm going to go 20K. It just sounds better. I'm going to divide by the 60. And it looks like I've got a quarter, or 0.25, whatever you want to call it. That's equal to e to the 20K. I'm going to take a ln of both sides. So ln of that quarter. That's going to equal 20 times K. And so when I tried that out, in fact, let's do it right here, right now in the calculator. If I go ln of 0.25 divided by the 20, looks like the K for this story is minus .0693. Okay, great. I've got just enough room to finish this off. The units would be kind of weird. They would actually be upside down minutes, because this 20 was in minutes. All right, we're done. The actual story here, I'll put it right here, the temperature at any time t for this piece of metal that's cooling, or this can of water, I guess it was, that's cooling off, it is going to be eventually 20. Right, we're heading for 20. We start off with this difference of 60 that's decaying away. E to the negative decimal 0.693 multiplied by t. And I think there was room to put this down below. Yeah, okay. All right, we'll put it in here again. 20 plus that original difference, 60. That's decaying away. And here's my room temperature. There's the A, right? And then that original difference in this story of 60 that goes away slowly. That's what that Newton's law of cooling is like. We can now do a couple of little Math 12 questions if you want with it. Right? So there's no more calculus to do here. Right? Like, oh, well, when will the water, be down to 24? Still a little bit above room temperature. There is no calculus in this story. Just some work with exponentials and logarithms. It's probably good practice, though. I'm going to split the page by a little more space. So I would say, oh, okay, well, I've got the machine ready to go, and I'm just wondering, when does that machine hit 24? And the machine is 20 plus 60 e to the negative decimal 0.693 times t. Now we're looking for t. So just a little Math 12 review. I'd move the 20 and say 4 is equal to 60 e to that k. Geez, it would almost be easier just to keep calling it k until you're really ready to use that number. Going to divide by the 60, right? So I've got 4/60ths, if you want to call it that. You can find out what that is as a decimal or a reduced fraction of 1/15th, whatever you want to call it. And then e to the, I'm going to do it. I'm just going to call this kt. It's faster. It's easier to write. I want to solve for that little t, so I'm going to take the ln of both sides, and I could say the ln of 4/60ths, yes, 1/15th, same thing. That's equal to that k that I don't want to be bothered to write out, multiplied by t. So it looks like t is going to be this ln of this fraction divided by negative decimal 0.693. And you actually get a double negative there, top and bottom, and it works out to be a positive, and it says you got to wait 39.069 minutes in order to get that to work. Okay, one more Math 12 question. There's really no calculus here. And then we're going to go and do an old AP question. This is actually going to be like Newton's law of warming. Just to throw something different at you, let's see if we can actually use this in reverse. A cold piece of steel, so it was in a freezer or something, is placed into a hot room that has a temperature of 36. So there's that room temperature again, right? That's the A right there. We're eventually heading for 36. They don't tell you what its temperature was right away, but they do say after 4 minutes, the temperature has risen up to 20. So it was colder than that. And then after a total of 8 minutes, in other words, kind of playing with the words here, okay, 4 more minutes. Right, total of 8. The temperature has now come up to 28, and they want to know what the original temperature was. Well, I'm going to dive right into the solution to this differential equation because I've kind of seen what it looks like, and I'm also going to split this page. I'm going to need some room to get this to work. Okay, so we've seen that generally for these stories, the temperature of the item, it's actually equal to room temperature plus some original difference, T0 minus A, and then the E to some KT, and the K is going to be a negative. We are looking for A, right? We're looking for, I said that wrong, we're looking for the original temperature T0. So we are trying desperately to find that number right there. It's the one thing that we're after. Well, let's start putting in some clues that we have. We're told that if you wait 4 minutes, the temperature of the item has come up to 20. So looking at that 4-minute mark, you'd have 20 is equal to room temperature, 36, plus T0 minus 36, E to the K, times 4. Okay, I'm going to just polish that up a little bit before I try the other clue out. I'm going to move this 36 by subtracting. So I'll have negative 16, that's okay, is equal to T naught minus 36 e to the, it just feels so much better to say 4k. I'm just going to call that equation number 1. Now let's go after the other clue. Okay, so I'm just going to grab a different color here. We'll go orange. The other clue says, well, if you go 4 more minutes, right, so 8 minutes from the beginning, then the temperature's up to 28. So we can say, okay, well, you're up to 28. That's equal to room temperature, 36, plus some original difference, e to the, now it was 4 more minutes, or a grand total of 8. So I could put in here k times 8. Moving it around, polishing it up just like before, I could move the 36, and I could say, okay, negative 8 is equal to T naught minus 36. There's really no calculus here, just some math. Just math 12. This would be 8k. I'm going to call that second clue equation number 2. And it's a good thing that I have 2 clues for this, because I have 2 things I don't know. I don't know T naught, and I really want it. And I don't know the k. And I'm willing to find the k if it helps me find the T naught. And I'm going to do that thing that we did just a second ago, where we go and stack up these 2 equations. Okay, I think we did it back 1 video ago, where we put one story on top of the other one. So I'm going to put equation 1 on top of equation 2. You could say, all right, negative 16 is equal to this. I really want that T naught. E to the 4k. And I'm going to stack that up on top of the other one. That equation was negative 8 and T naught minus 36 e to the 8k. And you can see why this is a great plan. This mysterious T naught over 36 goes away. And you're like, oh no, don't throw that away. I want that. Yeah, we're going to need to find the k first. Then we can go and get that. So cleaning this up, negative 16 divided by negative 8, just a pretty harmless 2. And then dividing. Well, if you divide powers with the same base, you have to subtract exponents. So 4k minus 8k, that's negative 4k. And right now my plan is, let's go get the k, and then we can use the k to find out the T naught. So I'm going to go up to the other side of the page here, and I'm going to take the ln of both sides. So I'm going to go ln 2, and then I'll have the negative 4k. All right, a little division, and I'll at least know what k is. So ln of 2 divided by this negative 4. Okay, got it. The k is negative 0.1732. I'd probably save that number into my calculator if I needed to use it again, and I do. The units would actually be upside down minutes in this story. It's always an upside down time. And now I could pick any one of the 2 clues that they've given me, and I could go and figure out what the T naught is. It really doesn't matter which of those 2 clues, which of those 2 equations I use. I can use either the green one or the orange one. It makes no difference. Maybe I'll go with the green. So I've got negative 16 is equal to, I'm just totally looking for that T naught. I mean, that T naught, that's the one thing that I'm trying to find, right? Going after that. So T naught minus 36 e, but now I know this k, right? It's 4 times it, so I'm going to have 4 times negative 0.1732. I've actually got upside down minutes and minutes that are canceling. That's beautiful. And what I can do is say, all right, what would that be? If I multiply that by 4, trying to keep all the digits I can, and then I'm going to go e to that. That works out pretty nice. That's just 0.5. That's no fluke either. Negative 16 is equal to this mysterious T naught minus 36 times 0.5. So I divide by 0.5, which makes the 16 get bigger, and I have negative 32 is the original temperature difference here. Okay, so negative 32, then I'm going to go and add 36, and I find out that the original temperature of that material when it came out of the freezer was 4 degrees Celsius. So you can even use Newton's law of cooling backwards as a Newton's law of warming. It's totally comfortable doing that. If you were to graph this, I got just enough room to do this. If you were to graph this, what you'd find is that it's like exponential decay, but we're heading towards room temperature, and room temperature is up here, and you'd actually have the temperature of your cold item start down there at 4, and then it decays up to it like that. It would limit out. If you were to wait forever for time and you were watching that temperature, you'd see it limits out to that room temperature again. Okay, enough with the temperature stories. At this point, we're going to go and do one last question in this booklet, and it is taken from an old released AP exam long answer section from 2011, and it says, at the beginning of 2010, landfill contained 1,400 tons of solid waste, okay, just material at the dump. The increasing function W models the total amount of solid waste, okay, W is for waste, stored at the landfill, and planners estimate that the waste, W, will satisfy this nice differential equation here. So dW dt, this is going to be the rate, right, at which we're adding waste to the landfill. It's equal to 1/25 times W minus 300. And that's going to work great for the next 20 years. Okay, so W is measured in tons, T is measured in years, starting at 2010. Awesome. It looks like this is some sort of interesting growth to this story. I don't know exactly how it's going to unfold, but I'm kind of imagining in my mind that there's a graph out there of waste at the dump and then time going by. And at the beginning, we start off with 1,400, right? So we're up here, 1,400 tons. And then it's going to grow, right? I don't know really, like, how does that graph look? Does it grow aggressively down? I don't really know. It looks like some sort of exponential growth, but it's got this minus 300 to it. So I'm kind of suspicious that, yeah, it's probably going to, maybe, go up like this. I don't really know for sure, right? It's a bit of a guess right now. So maybe I shouldn't even, put anything in just yet. We'll get to that. Part A. Use the tangent line to the graph of W at t equals 0 to approximate the amount of solid waste at the landfill after 3 months, after a quarter of a year. Okay, well, this is just your typical tangent line question. That's all it is. We don't need to know the full solution yet. Okay, I know that if I want to do a tangent line, if that's what they're asking me, then I've got to go and find a couple of things. I need a point on the graph, and I'm going to need to know a slope on that tangent line. Okay, well, they're starting us off with t equals 0. So they're putting us right at the beginning. Okay, there's the point. It's 0 and 1,400. So that's good. Time is 0. The waste is 1,400. What I do need to know now is what's the slope of that actual solution going to be, right? So I haven't seen the solution yet. Remember, I was kind of guessing that, maybe it goes like this. I need to know the slope, like right there. But that's where the differential equation works really, really, really well. Because they said, oh, well, if you ever want to know what the actual slope of that graph is, if you want to know what W prime is, it's actually just this is their story, 1/25 W minus 300. Yeah, I want to know what W prime is, figured out right at time is equal to 0. Oh, okay. Well, at time equals 0, I know that that's when the waste is 1400, right? Because this is the dependent variable. This is W, right? It's the only waste number that I know that when time equals 0, the waste does equal 1400. Okay, well, I can do this. That would be 1/25, and then I'd multiply by 1400 minus 300. Okay, so 1400 minus 300, that's just going to be 1100 multiplied by 1/25. Okay, well, how many 25s are there in 1100? There are 4 25s in every 100, and I've got 11 of these hundreds. So 4 times the 11, it's actually going to be 44. You could do that without a calculator. And if it was a no calculator section of the AP exam, you could just leave it as 1/25 times 1100. That's actually totally fine. Okay, the tangent line. All right, we can go find that tangent line. Sure, let's do that right over here. We can say W minus 1400 all on top of T minus 0 is equal to 44. Moving that around a little bit, we could say W minus 1400 is equal to 44 times T minus 0. I don't have to put the minus 0 on there. I can move the 1400. I can say, okay, here's a tangent line. It's going to be 1400 plus 44T. And then they had a request. They said, well, could you try working out on that tangent line where you would be at a time of 1/4 of a year? Sure, we can do that. So on that tangent line, if I go and put in, right on that line that we've got there, I'm going to go and put in 1/4, right? 0.25. It's going in for T. So I can say, okay, that'll be 1400 plus 0.25, 1/4 of 44. This is on that linearization, right? That linear line I'm using to estimate it. Well, 1/4 of 44 is 11. So that tangent line is going to be hitting 1,411 tons. Now, I don't know whether the graph right now is above or below that, but if I draw in this tangent line, what color did I have down there? Purple. Okay, so there's a tangent line in there, and it's got this nice slope of 44, and it's going kind of like this. And we just figured that if you went over to 0.25, that you'd be up at 1411. Okay, great. No worries. That was part A. That was doable. Now part B. They said, can you go and do a second derivative? Right? They gave you the first derivative in the differential equation. Can you go and get the second derivative? And you can write it in terms of W, they said. Well, that was nice of them. So we'll be able to do some, I don't know, whatever kind of differentiation works here to get that to work. It might be implicit, we'll see. And then use that second derivative to figure out whether our answer is too high or too low. Okay, I don't even know where they're going with that, but let's go and do this derivative first and see where this goes to. So I know from the differential equation that they gave me, they said, well, we'll give you this derivative, dw dt is actually equal to 1/25 times w minus 300. They said that. So what I want to do now is take another derivative, right, and see if I can get to the second derivative and see what that would look like. Now this is going to look a little sneaky, but I think we can pull it off. So I want to do one more derivative. It's like I'm saying, hey, let's do a ddt of this dw dt. They already gave you the dw dt. Let's do the derivative again of that, right? So our goal is to do a derivative with respect to time of this first derivative. So I have to do a derivative of 1 over 25 times w minus 300. Right? It's like, let's go and do this derivative. That would be this second derivative of w with respect to time. Okay, well, I'm going to cheat, right? So I'm trying to find this. And I have to do this derivative of that, and I'm looking at it, and I'm like, well, it's got w's in it. Can I do a w derivative instead? And the answer is, okay, sure, if you want. You know, this little bracket here, if you want to look at it a different way, this is like saying 1/25 w minus, and then 300 divided by 25 is just like a 12, right? So I'm going to do a derivative of that. And at first I'm like, oh, the derivative's pretty easy. It's just 1/25. Well, that was cheating. When I say, oh yeah, the derivative of that is just 1/25. I just did a w derivative. And I was supposed to do a t derivative. So I have to now multiply by the derivative of w with respect to t. I've got to do that to fix this problem. That's just the chain rule, saying, well, if you're going to do the derivative with respect to t, or with respect to w, and you're supposed to do t, now you got to go and do this. So how do I deal with that? And the answer is, oh, it's right up here. It's actually the differential equation, right? That's what dw dt is. So the long and the short of it is, the answer is 1 divided by 25 times 1 divided by 25 w minus 300. Okay, it's interesting. How else can I write that? I could say this, that d squared w dt squared, which talks about the concavity of this graph, it's actually equal to 1 over 25 squared w minus 300. And now they're asking me, once you've got that, can you use it to figure out whether or not that 1411 answer you had was too big or too small? Right? They're saying, what about your answer in part A? Well, let me go back to my little sketch that I was doing here. There's my tangent line, and I don't know, is the tangent line above the graph or below the graph? Well, it depends. If this graph actually, if the true graph is bending up like this, if it's concave up, then the purple line is too low. But if the graph in reality is like this, and if it's concave down for w, then the purple graph is too high. So I can really learn a lot if I just go and figure out whether the second derivative is positive or negative, right? How is that graph actually behaving? Because I don't even really know what w looks like yet. That's actually the final question. So let's go and see if we can figure out what the concavity of this story is going to look like. Is it positive or is it negative? Well, we've got 1,400 tons of the material. So if I check out the derivative at time 0, right? If I go and say, all right, at the very beginning, my d squared w dt squared, this concavity, it would be 1 over 25 squared, and then 1,400 is how we start, minus 300. Okay, it's looking to me like we've got nothing but positive numbers here everywhere. Positive, this is positive. That tells me that this answer for the second derivative is positive. Hey, our graph, w, that graph is concave up. So looking back at the picture, oh yeah, it's that upper picture. It's not this one. So that purple number we had, the 1411, that estimate of how much stuff there is in the landfill, that's too low. That's too low. So what was their wording exactly? Was your answer in part A an under or overestimate? I would definitely say that it was an underestimate. $14.11 is too low. Now the final question of this chapter Can you actually go and find the real solution to this problem? Because right now I was just, look at me, I was just sketching this thing, right? Like, I don't know, it kind of goes like that, it's concave up. Well, let's see if we can actually get the right answer here. This is a separable differential equation. It's hard, it's a tough question because the answer is hiding on that right-hand side, but it's totally separable. So we can take this and say, hey, separating the variables, putting w's on the left, 1 over w minus 300 dw is equal to 1 over 25 dt. Now we'll go and we'll integrate both sides, see how that works out. Not too worried about that right-hand side, that's going to be pretty easy. And this left-hand side, I've seen this game, right? We've seen this story that so looks like the logarithm deal, you know, where you have 1 over x and you're integrating and you go, oh, that's just ln x. This is just a little blob down there. Yeah, you could do antiderivatives by substitution if you want. You could say, let's let b equal that blob. But I've seen this enough. I know how this is going to unfold. This is going to turn into the ln of w. Well, you know what? Let's put absolute value bars on once just to be safe. It's going to be the ln of w minus 300 is equal to, this is going to be 1/25th t plus a c. And for safety's sake, let's go and grab some absolute values and put it on absolute value bars, put it on that argument in the ln. And now I'm going to check and ask myself, do I need those absolute value bars? You know, I always put them on at the beginning just to check. One of the numbers I saw was this 1400 number for W. And if a 1400 number went in right there, that'd be 1100. Oh, I do not need these absolute value bars, right? So I'm okay. You know, if you could look at it and say, you know, if you're wondering, what should I write? You know, to justify that, you can just say that you've noticed that W of 0 is 1400. Or you can say, hey, you told me this. And that tells me that W minus 300 is positive. I do not need the absolute value bars. Love to remove them. And I'm just going to say ln of W minus 300 is equal to 1/25th t plus a c. Great, but I don't want to look at the ln of W. I want to look at W. So I'm going to exponentiate both sides. W minus 300 is equal to e to the 1/25th t plus some sort of c. I really do not like the look of that c that's there. Never like that. So I'm going to regroup that. Plus I'll move the 300. We could say W is equal to 300 and then we're going to have plus, this is like an e to the c times e to the 1/25th t. And I don't like that e to the c, so I'm going to reposition it and say, okay, that's 300 plus some other constant, e to the 1/25th t. Now, obviously, those are not the same c, and if that bothers you, you can put little subscripts in there and say, well, that was constant 1, this is constant 2. That's an option, right, to do that. Other people would just say, hey, without loss of generality, we're okay. But if you are going to put the subscripts in, they kind of should stay now. I'm now going to go and find out what that constant is just by using the initial condition, because they told me that at time 0, there's supposed to be 1,400 tons of this waste at the landfill. So putting that in, 1,400 is equal to 300 plus this second constant. And then that would be e to the 0, right? At time 0. 1/25th times 0 is 0. E to the 0 is a 1. It looks like that c is 1,100. So we've got a final answer that looks like this. The amount of waste in your landfill at any time is equal to 300 plus 1100 e to the 125th t. That will let you see how much waste there is at any moment that you want to go and check. So it was a little tough. It was a separable differential equation, and we did that classic little move there of moving the constant to a much more convenient position. But we've come up with the right answer, right? That's going to be what the story looks like for the waste at this landfill. And that's the end of this lesson.